Hi statistics students, this is your video for Friday, March 22nd, and this is going to cover one topic related to the unit that we just covered, so operations with probability. When we come back together on Monday, we're just going to sum up our polynomial unit and just focus on some key takeaways and some key things that we want to improve moving forward. So about 2 more days of chapter 5 work, and then we'll move full steam ahead into chapter 6. So this is actually one of the topics in probability that I find the most interesting. And what we're going to do today is work with our two-way tables, which you've seen a lot before. You saw them yesterday on your quiz in the context of physics and engineering professors and representation, so gender breakdown. But specifically today, we're going to use the two-way tables to talk about what's called a false positive. So let's go ahead and get started with the original problem here. And let's see what we can figure out mathematically based off of the information that's provided. So this problem setup says a blood test was created to detect the presence of the Zika virus in regions where the virus has been identified. So the Zika virus was that virus that spread around in Latin America and South America and the Caribbean, and it was mosquito-borne illness. And so researchers were working really hard to figure out how to identify Zika and then how to prevent it from spreading. This problem then says, in Puerto Rico, 13% of the population of 3 million was exposed to the virus. A medical researcher claims that her test accurately diagnoses the presence of the disease with a rate of 92%. Given this information, what is the likelihood that someone actually has Zika, given that they obtained a positive result from the test? So our goal here, you guys, is that if you are a doctor or a nurse or somebody who's administering a medical test, when you get a result back that's positive and you tell that to somebody, you want that to be true, right? You don't want to go around telling people they have some really scary virus when they don't actually have it. So our goal here is to figure out what is the likelihood that that's actually going to happen. So for people in Puerto Rico, it says 13% actually have been exposed to the virus. So that means they're going to test positive. It's going to show up in their bloodstream. So what we can do is find that total numerically by taking 3, so 3 million, and multiplying it by 0.13. So if you plug that into your calculator, you're going to get 0.39. So 0.39 million people in Puerto Rico have been exposed to the Zika virus. So those are the people who have the virus in their bloodstream. Then we need to identify, are those people going to test positive or are they going to test negative? So the medical researcher says the test that she's developed has an accuracy rate of 92%. So of these 0.39 million people, what we can do is take that 0.39 and multiply it by 0.92. And this is going to give us the number of people who are accurately going to be diagnosed as having the disease if they have it. So we're going to have 0.359 is what I get. So let's round that to 0.36 from this value. So this operation was all of the people who had Zika in their bloodstream. These are the people who have Zika and are going to test positive. So if they're accurately testing it 92% of the time, that means that 8% of the time there is a chance that they are getting it wrong. So 0.39 times 0.08 is going to 0.08 is going to give us 0.03. So these are all of the people who actually have Zika, but the test is not accurately diagnosing it. So it's going to return a negative result, even though they actually do have the disease. So this is going to be a 0.03. Now the total, if we just add those together, gives us that 0.39 that we started out with, so 0.39 million. So that's everybody who has the virus and the information about whether or not they're going to be diagnosed or not. So then we need to figure out what's going to happen with the people who don't have Zika, who haven't been exposed. So 13% does have Zika or has been exposed. That means 87% do not or have not been exposed. So we can take the population of Puerto Rico, that 3 million once again, and multiply it by 0.87. If we do that, 3 times 0.87 is going to give us 2.61. So 2.61 million people do not have Zika, so don't have. But presumably those people are still interested in having medical tests if they live in a region where this virus is prevalent. So we want to see what happens if they take the test. What are their results going to be? So the accuracy rate is a 92%. So what I want to do is take that 2.61 and multiply it by 0.92. So 2.61 times 0.92 is equal to 2.4. So if they don't have the virus, an accurate test result is that it's negative. So that 2.4 is going to go right here. But then, just like we saw for the people that did have Zika, is that sometimes the results aren't going to be accurate. So if you don't have it, then getting a negative result is the correct thing to have happen. But 8% of the time, that's not going to happen. So we want to take our 2.61 million people who do not have or are not exposed to the disease and multiply it by 8%, so 0.08. And that's going to give us the proportion of people who get positive results, even though they don't actually have the disease. So this is the proportion I get for that value. So let's go ahead and round that to 0.21. So 0.21 million people do not have the virus, but they will test positive. And let's fill in our totals here. This total, people who don't have the virus, is 2.61. And then let's sum each of these columns. So 0.36 plus 0.21 is 0.57. 0.03 plus 2.4 is 2.43. And then our last column, 0.39 plus 2.61 is 3, the 3 million people that we're talking about. So our goal here, you guys, is to figure out if we get a positive result, what is the likelihood that we actually have the virus in question? So that is a conditional probability operation. What that's saying is, what is the probability that you do have Zika given that you get a positive result? So first, we want to narrow in on our total positives. So this is our total of positives. This is going to go down below this 0.57. And then we want to find the total people who have Zika that test positive. So this is going to be 0.36. So that's going to go up top in our numerator. So let's divide that out. 0.36 divided by 0.57, and you're going to get 0.6316, or 63.16%. So here's what that means in a real-world context. If you go to the doctors and you were to get this specific medical test for this virus, and you got a positive result, there's only actually a 60% chance that you have the disease. So you're not really guaranteed a whole lot of information just based off of one positive result on one single test. So let's go ahead and check that out in one more example. And then the last example on these slides we'll save until Monday. After you work through the second example, what you want to do is try the worksheet that's linked online. So this previous test was one that we were analyzing for the Zika virus. This next test that we're going to analyze relates to a specific type of lung cancer. And so this setup says a test for this type of cancer indicates that it's 98% accurate for diagnosing the presence or the absence of the disease. In a single population of 100,000, the incidence rate of this type of cancer is 3%. Given this information, identify a two-way table for people who do and do not have this type of cancer, and whether or not they will have an accurate diagnosis for this test. So the medical company is saying, hey, our test is 98% accurate. And as a bystander, being 98% accurate sounds really, really good. But because these diseases are rare, it's just going to be more likely fundamentally in a population that people don't have the disease than that they do. And so that's what affects that rate of false positives, is that the test is going to be relatively accurate, but more often than not, people won't have the test, and so that numerator gets skewed in that sense. So let's go ahead and do our operations or our calculations here. Test is 98% accurate. We have 100,000 people. Incidence rate is 3%. So we want to start off by figuring out how many people in total are going to have the disease by multiplying this by 0.03. And that's going to give us 3,000 people actually have this specific kind of lung cancer. Then it's 98% accurate for testing if you do have it. So if we multiply 3,000 by 0.98, that's going to give us the people who get positive results and actually have the cancer. So 3,000 times 0.98 gives me 2,940. So I'm going to fill that in here. So they test positive. And this isn't actually a virus, but a specific disease. So the lung cancer that is in question here. So 2,940 are going to test positive. So that means they're going to miss 2% of the cases where people actually have the disease. So if you multiply 3,000 by 0.02, that's 60. And so this total here is 3,000. So those are the people who do have this specific disease. Then we're interested in identifying information about people who do not. So if 3% of the people in the population are going to experience a given disease, 100 minus that value, or 97%, are not going to experience that disease. So what I can do is take my population of 100,000 and multiply by 0.97, and that's going to give me 97,000 people who do not have this specific kind of lung cancer. Then this test, like it says, is 98% accurate. So if I multiply 97,000 by 0.98, that's going to tell me the people who do not have the disease and also are told that by the test. So that's going to be 95,060. So they're going to test negative because they don't have the disease. And then the remaining 2% are going to receive a false diagnosis. They would be told that they have the disease even though they don't. So 97,000 times 0.02 gives me 1,940. So that's this result right here. And then my total here was 97,000. Overall, our population had 100,000. And then we want to fill in these other columns. So 2,940 plus 1,940. That gives me 4,880. And then over here, 60 plus 95,060 gives me 95,120. So once again, we're interested in that rate of false positive. We want to know if a patient is told that they have this type of cancer, what is the probability that they actually do? Because that's huge, right? That is incredibly life-changing and terrible information to receive. And so we want to make sure that when medical tests are offered, they are given information that doesn't have a super high rate of false positives or that multiple tests are conducted at one time. Because then if each test is independent, the likelihood of multiple results happening becomes less and less likely if a specific type of disease is not present. So in order to test this rate of false positives, we want to find the likelihood that someone has the disease, does not have the disease. Well, we can find the rate of has the disease, and then we can see how accurate it is. And that is given that they have a positive result. So our positive result total is this 4,880. Our numerator here of people who actually have the disease is 2,940. Divide that by 4,880. And so this is going to be 0.6025, or 60.25%. So if you receive a positive result on this test, there's a 60% chance that you have the disease, approximately, but also a 40% chance that you don't. So your homework tonight is going to follow along a very similar kind of setup for this problem. And then when we come back together on Monday, instead of talking about a medical test, we'll talk about a polygraph test, so a lie detector test, and see how that sense of false positives comes into play here.